Welcome to this video. In this video, let us solve one problem on multi-stage compressor. Now, let us read the problem. In a two-stage reciprocating air compressor, now we are talking about a problem with two-stage. So, we can draw a PV diagram for two-stage reciprocating air compressor, but let us see whether we have a clearance volume or not. Okay. With intercooling, there is intercooling. The pressure and temperature at suction is given, okay. Delivery pressure is given, intermediate pressure is given as optimum value, okay. It is given that the compressor saves 13% of work required, okay, working between same suction and discharge pressure. Calculate heat transfer, okay. So, that means this is a problem of multi-stage air compressor, but however, there is no clearance volume. So, I am drawing now the PV diagram for a multi-stage air compressor. Now, this is without clearance volume. So, we will have two stage. Okay. Now, this is our first stage compression, then there is intercooling. So, this will be our second stage compression. Okay. This is our second stage compression. So, now 1 to 2 we can call that as first stage compression, then 2 to 2 dash is intercooling, then 2 dash to 3 is our second stage compression, then 3 to 4 is our delivery in the second stage, and we are coming back to the initial pressure by the process which we are denoting here. So, this is our intermediate pressure, intermediate is equal to P2. Okay. Similarly, delivery pressure is P3 is equal to P4. All right. So, similarly, the suction pressure is P1. Okay. So, this is what has been given to us in a two-stage reciprocating air compressor, intercooling with intercooling. So, with intercooling he has mentioned, but he has not mentioned what is the intercooling temperature. So, we will assume that there is perfect intercooling. What does that perfect intercooling means to us? Intercooling perfect means after compression from 1 to 2 the temperature would have increased, but we are circulating cooling water around this compressor. So, we get our circulating cooling water around this air. So, we bring back this temperature T2 to T2 dash, which is nothing but T1. So, we will bring it back or cool it back to initial temperatures. So, for a perfect intercooler, so which means intercooler can cool it back to initial temperature. So, T2 dash must be equal to T1. Okay. That is what perfect intercooling means. Because he has not mentioned anything about intercooling temperature, we are assuming that it is a perfect intercooler. Pressure and temperature of air at suction are given 1 bar and 37 degrees Celsius. So, P1 is 1 bar and T1 is given as 37. Let us convert it to Kelvin. 37 plus 273 is 310 Kelvin. Okay. The delivery pressure is 12 bar. So, delivery pressure according to our diagram is P3 is equal to 12 bar. Now, do not worry about the numbering. Different books may number it differently, like they may start this as 2 dash as 3, 4 and 5 and 6. It does not matter, as long as you understand the cycle, it is okay. So, delivery pressure according to our cycle is 12 bar. It is the intermediate pressure is at optimum value, that is very important. We had this derivation. So, intermediate pressure or P2 is equal to square root of the suction pressure multiplied by delivery pressure. This derivation we have done. So, P2 can be found out by this technique. Okay. It is given that this compressor saves 13% of work compared to single stage compressor working between same condition suction as well as discharge pressure. So, remember that means if we had continued this process So, now what we have done, I mean to say, we have compressed from 1 to 2, then intercooled it, then 2 dash to 3 is our second compression. Now, had we done this compression in a single stage, we would have got this much of work, because area under the curve in a PV diagram gives us the work transfer. Now, so remember that is also the need for multi compression can be defined here. So, area under 1, 2, 3 dash, 4, 5, 6, 1. So, this is what? This is actually single compression between same suction pressure P1 and P3. Had we done that, we would have got, I mean, this much will be more. I mean, the hatched line, that much will be extra, correct? Because now what we have done is 1 to 2, 2 to 2 dash. So, new that is multi-stage compression is what? 1 to 2, then 2 to 2 dash, 3, 4, 5, 6 and then back to 1. Now, area under this curve is relatively smaller. How much is that? That is what this hashed area is showing. Now, this is what he is saying, that this is 30% less. I mean, if we do the same compression by a single stage, we would consume 30% more work compared to the multi-stage compression with intercooling. So, the actual cycle which we are talking, is, now this is just a proof, why multi-stage compression can save energy. So, this is answer why multi-stage compression can reduce work input. So, because area under the curve is the indication, area under the curve shows that there can be some amount of work can be saved if you go for multi-stage and with also intercooling. Now, let us go back to the question again. We are asked to calculate the heat transfer, that is heat transfer per kg of air in the intercooling. So, intercooling is MCP, because constant pressure Cp T2 minus T2 dash. If we can find out this value of T2 and T2 dash, we will be able to find out the value of amount of heat rejected in a intercooler. Now, let us find it out. Now, T1 is given, so this is nothing but T2 dash as we have discussed intercooler. Now, if we find out T2, that will be fine. Okay. Now, in order to find out T2, I think we need P2. So, let us get the value of P2. Now, P2 is equal to square root of 1 into, so that is P1 is 1 and this is 12. Now, if I substitute this in bar, it is not a problem, because there is no unit. So, we will get the answer in bar only. So, no need to worry about unit balance. Let us solve this equation. Square root of 1 into 12. So, that is 3.464 bar. 3.464 bar. That will be our intermediate pressure P2. Now, if P2 is known, let us go for T2. Now, how do we find out T2? We know that this process is PV power n is equal to constant. Now, P1 V1 power n is equal to P2 V2 power m. This is because process 1 to 2 is polytropic, that is PV power n is equal to constant. But we do not have volumes, it is better we replace this volume by temperature. Now, how do we do that? PV is equal to MRT, we know, and volume can be written in terms of MRT by P, or since M and R gets cancelled out, we can substitute temperature and pressure, that is T by P. So, P1 T1 power n by P1 power n, that is what we mean. So, here also P2 T2 power n divided by P2 power n. Now, this can be further simplified T1 power n, P1 power n minus 1, now T2 power n divided by P2 power n minus 1. Now, we are interested in finding out T2. So, I will keep T2 by T1 this side whole power n. So, P2 by P1 on this side whole power n minus 1, and we know that this will be T2 by T1 P2 by P1 whole power n minus 1 by n. Or we can also say that T2 is equal to T1 this pressure ratio, intermediate pressure divided by suction pressure whole power n minus 1 by n. Now, I think we know T1 310 Kelvin, and we know intermediate pressure we had got 3.464. We need not to bother about converting it to Newton per meter square, because we know that 10 power 5 cancels out. Now, P1 is 1. Now, whole power we have not been given the value of n. So, let us assume the polytropic index n is equal to 1.3. Now, that will be 1.3 minus 1 divided by 1.3. Now, let us calculate T2. So, 310 into, so the 3.464 divided by 1 will be same 3.464 to the power 1.3 minus 1, 1.3 minus 1 divided by 1.3. So, 412.93 Kelvin. So, T2 is found out now 412.93 Kelvin. Now, once we have found out the value of T2, I think now we can go back and find out Q value, because Q is equal to Cp. Now, Cp for air is also known to us. Cp for air is 1.005 kilojoule per kg Kelvin. Okay. Now, Cp is 1.005, Q is equal to Cp. T2 minus T2 dash, that is 412.93 minus, now what was our T2 dash, that is initial temperature 310 only. So, 310. So, we are doing it for 1 kg because mass is not given to us. So, this was substituted in kilojoule per kg Kelvin, and this was in Kelvin. So, Kelvin goes off, we will have the unit in kilojoule per kg. Okay. So, 1.005 into 412.93 minus 3. So, that will be our answer for heat rejected in a intercooler, 103.44 kilojoule per kg. So, even though the work saved in the multistage is given, that is not useful here, because what has been asked can be found out without using that 13% of saved energy. So, this is our heat rejected in intercooler. Now, let us solve few more problems on multistage compressors in the next class. Thank you.